Alright, so let's get technical. So for this part I'm going to assume that people have a basic knowledge of 3D game development, 3D terminology. And this is important because there's a lot of new stuff in FlashMolehill that wasn't there in Flash 2D. So I'm just going to assume that basic knowledge. Okay, so I'm going to talk about a lot of things, starting from display with the display layers, and then I'm going to talk about all the file format optimization that we did to create big 3D game, and character animation, which is very important in Zombie Tycoon. Particle system, how did we manage it? How did we make a system that could have a thousand of particles? And then lights and shadow. Those are very important in Zombie Tycoon because it is a very dark game. The scene is very dark, and we needed to amplify all the effects. So light and shadow is very important in Zombie Tycoon. Then CPU post-processing effect, how it is possible to take what is rendered on the GPU and do CPU stuff with it. And finally, I'm going to talk about the tools available for classic profiling and also for the new 3D profiling and debugging. So what tools are there? Finally, I've joined a couple of bonus slides on the 3D game dev lexicon. There's a couple of all the maths, which there's a lot of numbers in all the slides, and all the maths are at the end to answer, well, how did we get to those numbers. And finally, there's some cheat sheets on Molehill and Molehill API. Alright, so in Molehill you have a couple of layers that you can use. The one on the very back is the stage video. So the stage video can play hardware accelerated video like H.264 and other media types, but it's on the very back, and it is not transparent, so you can't see the web page behind it. Same thing with the stage 3D, which is just on top of the stage video. It is also opaque, so there's no if you have 3D content and video, the 3D content will always be on the top. And finally, there is the classic 2D stage display list structure, which is on the very top. And as you can see in the Zombie Tycoon, so on the left part, in the intro video, we made the video in the background, and there's some UI on the top. Also in the game on the right, you have the game which used the stage 3D, but not the stage video. And there is, of course, the 2D UI made in Flash IDE on the top. So those are the results we can achieve. And then the file format. So we used we tried a lot of engine before starting our own, and most of the engine that we used, we're targeting colored XML file or generic file format, or 3ds, OBJ, MD2, and there's a lot of other common format, but they were all created to support a lot of people, and that wasn't the case for us. We wanted a format that would enable us to create big games and that would load very fast. So we made a format that was very small, that has almost no memory footprint, and that require no processing, which is very important when you have a lot of files to load. So in comparison, on a low-end computer, when we tried loading colored XML file, it was taking up to 5 seconds to load a model, and it just doesn't make sense. So when we use our own format, it was taking 15 milliseconds, and that is a big difference there. So what we do is we take assets from 3ds Max, we export it using Max script exporter to colored XML. Then we load that into our air tool, which parse all the colored XML file and fill the game object, the final game object that are going to be used light. So what we do then is, with the same tool, error tool, we serialize using native serialization, so with AMF, and then we compress using native compression with the byte array, and that gives us the game file. So it's a pretty what you see is what you get pipeline. So that is generating the game file. And of course, when you're in game, when you load the game, you just have to load that game file, uncompress it, unserialize it, and you have your game object, and then it's just ready to draw. So it's very easy. You just have to add it to the scene. It's a code snippet there, on model loaded, you can see. So you just have to do uncompression, native unserialization, so read object, and then you have it. You have your model loaded. Very easy. For texturing, what we did at first in Zombie Tycoon was to use PNGs everywhere. So all the texture in the game were in PNG, and the nice thing is, of course, the PNG are small on the disk. They are compressed file format, but when they are uploaded to the GPU, to the video memory, they are expanded as bitmap. And when you have a lot of texture, it's going to just expand and become very big, and that might cause problem. You might have a slowdown because of that. So Adobe has created a file format for that, which is called the Adobe Texture Format, so ATF. And one of the main goal is to use compression that are supported on the GPU to keep the texturing compressed on the GPU. So there's a couple of main encoding for that. So DXC1, ETC1, PBRTC, those are common format, and the other goal is to have a native support for multi-device or multi-platform publishing. So that's why they created the ATF format. So what is the ATF format? It's a composite of three of the main compression file format that are there: DXC1, ETC1, PBRTC. They are Adobe has created a tool that just use a PNG as an input and output ATF file that have the three format in it. So the ATF file is really a file with three different content in it. So on the disk, it's going to be bigger than your PNG because there's three compression format in it. But when it's loaded on the flash player is going to know what your device is, and it's just going to use the best one for your device and let go the two others. So on the video memory, in the video memory, it's going to keep the good one, and it's going to still be compressed on the GPU. So it is one big advantage. Also, those format contains the mapping of your texture, so you don't have to process it with the CPU as we did with the PNG. So it's a pre-process. It's a pre-process operation and not a live operation. One of the problem is the ATF format doesn't support transparency, so we have to manage it in other ways. So what we do is, for texture that require transparency, like the fans here, we use PNGs with indexed color. There are other techniques such as sampling an alpha mask, so two ATF, opaque ATF texture, one of the texture itself, and one which is a mask that you apply the alpha with. So that is two options, and there you go. So there's also ways to have texturing that doesn't require, that you might think it requires transparency but really doesn't, such as splatter and particle like effect like fires. So for the splatter, it's a multiply blending operation. So it can be compressed on the video memory, it can be an ATF file, because there's no transparency. It's a blending operation. It's a multiply. And the same thing with the fire. You just it's an additive, so you can't just add one particle over the other and the black background is just not going to sum up. So you don't need transparency for those. Character animation. So in Zombie Tycoon we had a lot of animation models and everything, and we needed to have a system that would support, well, animation. So there's a few techniques. Two of them are matrix linear blending and dual quaternion blending. At first, when we created the Zombie Tycoon, we started with the obvious matrix linear blending. It's pretty common, it's fast to implement, it's fast to run, and it just worked great. And the constraint linked to that in Molehill is the vertex constant shader, the vertex shader constant limit. So right now it's 128 floats, which limits the matrix to around 40 bones per character. One of the problem with matrix linear blending is the loss of volume, deformation. You might have deformation when the joints are extremely rotated, and that can cause what you see on the left side of the image. It's some kind of artifact, visual artifact linked to the matrix linear blending. And at some point, the game designer wanted to have not only character animation but animation transition. So going from idle state to walk state, or from walk state to dance state. So how were we supposed to do that? It is possible to do it with matrix linear blending. The problem is you require a lot of vertex shader constant to do that. As I was saying, so the matrix, by definition, matrix, for each bone you require one matrix of which is 3 constant, and that is give the maximum number of bone in the constant shader constant, and the vertex shader constant is 40. For the dual quaternion it's 60. So what happens is for our outer, which is for the zombie, which have 24 bones, we were okay with 2 choices. We could go with the matrix or the dual quaternion. And when it comes up to create transition or bullet time animation, which require frame interpolation, you have to have 2 full set of bones, and this led us with dual quaternion was okay with that, but matrix linear blending required too much constant, and hence we had to go with the dual quaternion to support transition. Another way is to create small animation that goes between 2 others. So create a walk animation, a walk to idle animation, and an idle animation, and we didn't want to go that way, so we went with the dual quaternion. Some of the other aspect of other points that compare dual quaternion to matrix is that when we implemented it, dual quaternion files were bigger than the matrix files, which might seem weird because they use less constant, but it is because the matrix are repeated a lot. There's a lot of stuff repeated from one to the other, where in the dual quaternion you don't have that, so the compression ratio is way better for a matrix than the one with the dual quaternion. So at the end, the dual quaternion file was 20% bigger, and it was just weird to find it out. You have also the vertex shader assembly code required to process those 2 kind of animation, those 2 techniques. So the dual quaternion is a lot heavier than the matrix shader code, and this make the dual quaternion processing heavier than the matrix processing. So it's about, from our benchmark, it was around 30 to 33% heavier to process in the vertex shader to process the dual quaternion to the matrix. So for the particle system, well, in that screen you can see a lot of particles. There's the shells that are particles. You have smokes and fire. The health bars are also particles, and that's just one example. So what we did is use a divided workload system. So we do some process on the CPU, we manage a particle on the CPU, and we apply the modification with the GPU. So on the CPU we update all the particle properties, alpha, color, direction, the frame if it's a sprite sheet. On the GPU we just apply all the main properties, and we also expand the vertex if it's a billboard. So that is one big optimization that can be done, is to set all the position of all the vertex of one particle to the same point and extract it on the GPU. So the GPU, after the world transformation, is going to be able to expand those vertex to their final position, and that is a big gain in performance compared to if you do the same thing on the CPU. So in Molehill we tried to we did try to show a lot of particles, and it's what you find it to do, but the main limits are due to the vertex buffer and index buffer limitation. So in theory you could have a lot of particles. In Zombie Tycoon we were limited to around 16,000 particles, and in the slides at the end I'm going to show some math of how many particles you could get in theory, but in Zombie it's 16,000 per drug call. So we also use fast binaries, also known as alchemy memory or domain memory, or there's a couple of other names for that, and we used Azot, but there's also PDSI from Joe Ibert and Alchemy, of course, that can play with those special opcodes. So when using Azot, the property update phase on the CPU, we gained about 10. We were about 10 times faster when using Azot than when we weren't. So it's a huge optimization that need to be done if you have to update a lot of particles. We also do draw call batching per texture. So we set one texture and we do all the draw of that texture at the same time. So for all the small particles that are in a scene, let's say the small particles, so anywhere they are in the scene, they are going to be rendered at once in one draw call. So there's a pool for each particle type for each texture. Finally, we tried also to have a full GPU particle system, something that would not use a CPU at all, and it is possible to do, and we were able to do it. It's the thing is, you have to create a system that would will update the properties in function of time. So using the span time and the current time, you can always say, okay, well, what are the position I'm supposed to be, the color, transparency, the fade out, and everything that can be defined as a linear transformation over time is can be used in the GPU, full GPU particle system. In Zombie Tycoon, the thing is that we were already GPU bound, so going that way would require a lot more of GPU time, and well, we hadn't anymore. So we choose to stay with the more balanced version, CPU, GPU. Again, a screen with a lot of particles, smoke, fires, a bar, and everything. And if you wonder what can look like 16,000 particles in one draw call, that's what happens here. So we cast a lot of shells, particles, and we kill a lot of zombies. I was talking about splatter before. you have the splatter here on the ground, so it just fade out, multiplying with the ground. So I was saying that in Zombie Tycoon it's a very dark scene and we needed a lot of lights. There's many techniques for that, so shadow map and light maps, dynamic lighting, fake volumetric lights, and fake projected shadows. Shadow map and light maps are pretty common 3D techniques for using lights on ground and object. You have one diffuse texture, one shadow map, a light map, and a composite, the final composite. So the maps are pretty simple. Diffuse multiplied by the shadow map added to the light map gives you the final image. And for all objects that are moving in the scene, avatars and dynamic object, we sample those object color with the shadow map, and it's going to make the avatar or the object go darker or brighter depending on where they are in the scene, and it gives a very great effect for very low cost in performance. And for dynamic lighting, at first we in Zombie Tycoon we first implemented the dynamic lighting, so create a lot of lights. Every object could sample 7 to 9 lights, and it was very nice, truly. But the thing is, dynamic lighting is very heavy, so when you have 7 to 9 lights per object, your object pixel shader code is going to go up to 256 instruction, which is the limit. And when it comes to that when it comes that big, it's just going to slow down the whole process, and it is very heavy on the GPU time. So we needed to find something else, and we kept the dynamic lighting, but we had to but at the minimum, and we had to try something else. So here's what dynamic lighting can look like. You can see it on the fans. The barrels are showing the lights, and you can see it on the avatars. Everything is the light is gradient and just in function of the distance and everything. So yeah, in the car it looks nice. So here's some shader code. So that is the point light and spotlight assembly code for only one light. So if you take the spotlight with 17 lines, it's a basic spotlight, so with no normal variation nor specular mapping and everything. So it's very basic. So if you say you have tens, a dozen of those, well, you're already very heavy on pixel shader code. So what we did is create volumetric lighting, fake volumetric lighting using particles. So on the top left of the image, you can see that for each street light cone, you have around 6 particles that are positioned in a way that looks like a cone. And on the right, top right, you can see that there's a lot more overdraw than with classic dynamic lighting, because the objects are not sampled with the lights, but there's a lot of layers of particles in there. The particles are also additive, so if your avatar or object is moving behind or under the lights, it's going to look brighter because it's additive, but it's going to also look brighter if they are under far behind the light. So there's some problem with that. And on the bottom right, there's the final composite image of the volumetric lighting for the street lights. It looks very good, even more in Zombie Tycoon, because it's kind of foggy and it just looks great for that scene. So this is what it looks like, volumetric lighting with the animation. So the same trick where was applied to the police cars lights, and we just move the particle around in circles, so it just, again, it looks pretty clearly. We use a similar trick for the projected shadow, so instead of casting a real shadow of the avatars or the object from another point of view to the ground, we created particles aligned to the ground, which are only circle, gradient circle, and we position, stretch them, and make them back facing the lights. So for every light source, depending on its position and intensity with the object, we're going to cast one of those fake shadow particle, and it just looked very good. In that video you can see the avatars going in a minefield, and for every mine that explodes, you can see those particles on the ground, which are looks very good. And CPU post-processing effects. So in Molehill you have the possibility to go and take what has been rendered on the GPU, take it back to the CPU, and do stuff on it in a bitmap data. That is strongly not recommended, and this is because the pipeline from the CPU to the GPU, from system memory to the video memory, is very fast. The pipeline for the inverse is very slow, and it can slow the whole application by doing that. It's a not recommended pipeline. Still, if you need to have it, or you want to do great effects such as bloom, motion blur, depth of field, or many other kind of effect, there's a way to do that. So on the bottom left, you have the motion blur. We're zooming in, and that is the motion blur. On the right you have a blooming effect, so on the top it's in the normal image, but on the bottom it's a bloom effect, so we intensify the light source everywhere in the scene. And the tools, so those are the classic tools for Flash as we know it. There's FlashGamingSummit, which is an open source software. Most of the production of Frame use FlashGamingSummit. It is very easy to use, it is free, it is now with the debugging profiler, it's very efficient, it's a great tool. And then you have Adobe Flex Builder Profiler, which can profile function calls and memory. You can do memory snapshot and comparison, and it's very easy to use when you're working on your project. There's Flash Preload Profiler, which is again an open source tool that I've made, and which is accessible in my blog. The links is at the end, but it can profile function calls, memory allocation, the loader status. So if you have files loading and you don't know what's going on, you have profiler telling you what are the problems, and it can be used in debug or release in the browser or in the project, or it can be used on any Flash application and at any time. So it's a great tool for that. For the GPU or 3D profiling, there's a couple more tools that are less known from the Flash community. One of those is Pix. So Pix for Windows, it's a part of the Microsoft DirectX SDK, and it is mainly a debugger tool. So if you're having problem rendering your scene, if you don't know what's going on and there's some problem, you can always go to Pix, and it's going to this the API call. You can validate everything in there. You have the shader code that you can see that everything has been processed the way it should. There's a pixel debugger. You can select one pixel on the screen and see all the steps that has affected that pixel, and you have texture viewer and a lot of other things. So Pix is really a debugger. There's also Intel Graphic Performance Analyzer, GPA. where Pix is more of the debugger, GPA is more of performance analyzer. So it can profile and find bottlenecks. It's very easy to find bottlenecks with it. It can render wireframe and overdraw and a lot of other modes. You have the vertex shader. You can sample one frame and modify shader, do experimentation. You can play with scissor rec and a lot of other options, and reprocess the time of rendering for all the object or one object, or you can play with the scene the way you want, and it's a great tool to find bottlenecks. So finally, here are their source and references. You have our contacts. As I said, you have the lexicon, you have the math, and you have some cheat sheet available there. All of those information I just kept are going to be available to download on our website. And thank you. So, is there any questions?